Yes, students, next problem. A steel rod 1.5 meter long has to resist longitudinally an impact of 2.5 kilonewton falling under gravity at a velocity of 0.9925 meter per second. The maximum computed stress is limited to 150 MPa. Find the diameter of the round rod. So you also go through the question once again. So let me draw the rough diagram. So how does it look? So let us take this as a steel rod. Okay, and this is having a length L is equal to 1.5 meters, suppose, has to resist longitudinally an impact of 2.5 kilonewton. So some weight is falling, right? So what is the weight of this? W is equal to 2.5 kilonewton. So this weight 2.5 kilonewton is falling on this vertical steel rod, and this is falling under gravity. See, falling under gravity, very important, students. This weight is falling under gravity with a velocity of 0.9925 meter per second. So if this data is given, means there has to be some meaning for this, right? Maximum computed stress is 150 MPa. Find the diameter of the round rod. This rod, you see, what is the diameter of this? That's what they are asking. Okay. So first of all, let me write the given data. So L is equal to 1.5 meter, that is 1500 mm, right? So next, what else they have given? Maximum computed stress is limited to, means when this weight falls on this rod, there will be impact stress, right? So that stress is nothing but 150. So you know what is the symbol? Sigma dash is equal to 150 MPa. So this is what they have given. And W weight is equal to 2.5 kilonewton. That is also given. So 2.5 into 10 raised to 3 newtons. Correct? And what else? Yes, students? Anything else is given? Velocity V, this is falling with some velocity V is equal to 0.9925 meter per second. So that's it. This data is given to us, right? Now let us look at what we studied so far, then we'll come to this, what is the use of this. So we already know now what is impact stress expression, which we derived, and also we solved numericals on that previous class. Impact stress sigma dash is equal to W by A into the bracket 1 plus square root of 1 plus 2 HAE divided by W into L. So this is what we have solved, right? And in data and book, it is equation 1.47, that is also told to you. Okay. Now in this case, W is known to us. Area is not the point, because cross-sectional area of this rod pi by 4 d square. But we want diameter, so this is also unknown to us, right? So Let us write what is area here. Cross-sectional area of a rod, that is pi by 4 d square. This d they are asking, let me write here, this d. What is this d? They are asking in the question. Okay. So W is known to us, this is known to us. What is not known is Young's modulus and height h. Right? Now, in this case, Young's modulus is not given in the question, right? But they have mentioned a steel rod, right? Now, if they don't mention Young's modulus, you can just go to data handbook, page number 18. This is design data handbook, page number 18. You have properties of materials. So there are two types of steels. So you take any steel. What is the Young's modulus? 210 GPa. So this will take, okay. Table 2.1. So E equal to 210 into 10 raised to 3 MPa. Table 2.1, page number 18. Okay, page number 18. So usually they give, but if they don't give, they will be giving us material. So based on that material, so you can search in the data handbook and you can assume the Young's modulus. Okay. So this is also we have found based on the material given. Now what is h? H is not given. What is the height from which this weight is falling on the rod? So that is not known to us. So how to find? Observe this. They have given some data. This weight 2.5 kilonewton falling under gravity. Falling under gravity means it is free falling case, right? This weight is free falling case at a velocity of 0.9925 meter per second, right? So you might have known the relation from engineering mechanics or PUC 1, 2. You studied this. What is that relation? V square is equal to U square plus 2AS. Alright? S is this distance, acceleration due to gravity, initial velocity, final velocity. Falling under gravity means U is equal to 0 because free falling. Right? Now this term will automatically become 0. So what left is V square is equal to 2A. So S means distance. So here it is height h. So let me take h. So velocity V is known to us, right? So what is that? 0.9925 the whole square into 2. So A is acceleration due to gravity 9.81 into h. So what is the height h now? If you solve, so we'll be getting 50.2 mm. Okay. So let me just correct it. So this is in, I think it is in meters. So h you'll be getting 0.0502 meters. So if you convert this into mm, so then you will be getting 50.2 mm. So this is the height h. Okay. So this is the use of data, students. This to know that this height from which it is falling. So basic physics you might have studied. Right? Under free falling case, initial velocity is 0 final velocity is given to you, v square is equal to u square plus 2as. So s here is distance, that is height h. So that's how we'll get height h. Now look at the expression, everything is known, this is known, w is known, h is known, Young's modulus is known. So if from putting all the values in this expression, you'll be getting cross-sectional area. Equating that value to pi by 4 d square, you'll be getting diameter d of the round rod. Okay. So I hope you have taken these things. So let me remove these parts. Okay. Now we will go on substituting the values in this now. So it is 150, which is equal to w is 2.5 into 10 raised to 3. So let me put as it is cross-sectional area A, square root of 1 plus 2 into, what is the h you got just now? Yes, 50.2 into cross-sectional area A. And Young's modulus also we have got from data handbook, that is 210 into 10 raised to 3 divided by w is 2.5 into 10 raised to 3 into length L, 1500. Correct? Now in the last class also I told how to solve this. Yes. So either you square both right hand side and left hand side, you squaring both sides, or simply you put in calculator. So A cross-sectional area A equal to 1595.11 mm square. This is the cross-sectional area of this rod. If you take a section throughout this rod, you'll be getting this area. Equate this to now pi by 4 d square. Cross-sectional area is pi by 4 d square of circular rod. So 1595.11. So if you solve this, so diameter of the round rod you will be getting 45.066 mm. So this is your answer, students, for this question. So very simple, but if you are good with mechanics, you can easily solve. It's the same expression you are using. So in the previous problems, directly h was given, directly Young's modulus was given, but here there are some alternative data is given. So based on that data, you have found h, and using data handbook you have found Young's modulus for the steel material. Substituting, you have got finally diameter of a round rod. Okay. Next problem on a direct load type. A sliding weight 1 kilonewton falls onto a flange at the end of a vertical circular rod of a length 3 meter. The diameter of the rod is 22 mm and is made of stainless steel. Assuming Young's modulus 200 GPa, assume no losses of energy. Find the height through which weight drops in order to produce stress in the bar of 150 MPa. So this is your impact stress. Also determine the elongation of the bar due to impact. So basic figure, let me draw. So by this time you are already aware. So how it looks, right? So this is the weight W which is falling on this, right? And there will be some deflection. So you already know these things now, right? Length. So that also I'll show. Yes. So this is a sliding weight. So let me write the data. W is equal to 1 kilonewton. So 1000 Newton. Right. So next data. Rod length L is equal to how much? So 3 meters. So 3000 mm. Diameter of this rod D is given. Diameter of rod is how much? 22 mm. And the stress 150, that is impact stress, sigma dash is equal to 150 MPa or Newton per mm square, and Young's modulus is 200 GPa. If they don't give, then take it from data and book. Anything else they have given? Okay, that's it. So first what they are asking, height through which this edge they are asking. So let me write the relation what you know, W by N. So it is familiar to you now. Square root of 1 plus 2 HEA divided by W into L, right? Now what is the cross-sectional area, students? Cross-sectional area is pi by 4 d square. So d is 22. So if you substitute 22 square, so you'll be getting as 380.13 mm square. So this also will substitute. So all the data is known to you. So substitute in this. So 150 equal to 1000 divided by 380.13, 1 plus square root of 1 plus 2 h, because this is what we are going to find. Young's modulus 200 GPa is there, into 10 raised to 3. If you do, it is in Newton per mm square. 380.13 divided by 1000 W into L. Squaring both the sides, or directly you can put the equation. So height h is equal to 61.9 mm is the answer. So first point is clear to us now. So this we have found. Next they are asking also determine the elongation of a bar due to impact. This delta I, once this weight falls on this, deformation or deflection will be there. So this is what they are asking, right? So first part is clear, very simple. So you can make a note of it. Okay. So then we shall proceed. So next they are asking what is delta I, deformation, right? And this deformation is due to impact. This is impact stress and this is a deflection due to impact load. So all this, go through the theory part, so the symbols will be clear to you much clearer way. Okay. So how to do it? Now first I already shown you while deriving this equation, but still I will write few steps. So see here, first of all the stress is directly proportional to strain, right? Stress is directly proportional to strain. So let me write symbol E, right? It is directly proportional to strain. What is strain? Strain is change in length or deflection delta I by L. This is your strain. Alright. Now I can say that the stress is, looking at this equation, and these are the basics you should be knowing. Looking at this and this, stress is directly proportional to change in length. Now this somewhere I am going to use. I will show you how to use. Okay. So make a note of these things. This is change in length. Strain is change in length upon original length. This is Hooke's law. Stress is directly proportional to strain. Right. So comparing this and this. So this relation we have got. Now look at this and what changes I will make. Look. So this is there. W by A, what is this? Go through the theory part which we discussed. It is static stress, right? 1 plus square root of 1 plus 2h. Now 2h, now see here what arrangements I will make. This EA I will take here, WL by EA it will become, right? WL by EA is nothing but 2. This is EA by WL, same thing. If I take WL by EA, so what is that? Yes, WL by EA, that is nothing but static deflection. So this I wrote in the lecture number 1 of this impact chapter. So this I have already shown. Okay. So static stress is WL by EA. Okay, why I wrote is it is required. Now see here what relation you have got. Stress is proportional to your deflection, right? Now only this relation or this relation you have in data handbook. Now you, by using this direct relation, how I will write, just look. So delta I, right? This is your impact stress. Okay, impact stress is directly proportional to this instantaneous deflection. So that's what I am writing here. And static stress is directly proportional to static deflection, right? So static deflection. This will remain as it is. Okay. This relation you are going to use to find this second term, elongation of the bar due to impact. Okay. I hope it is clear. So I will explain once again. Your impact stress is proportional to strain, right? What is strain? In this context, it is, this strain is deflection or change in length upon original length, right? Now comparing this and this relation, your impact stress is proportional to instantaneous deflection or simply deflection, what I have shown. This relation we already got by rearranging the terms in terms of deflection. Instead of, in place of impact stress or instantaneous stress, instantaneous deflection because of this relation. So instead of static stress, you have static deflection, and this will remain as it is. Okay, so you don't find this in data handbook, but that's how we find this relation to find this value, determine the elongation of the bar due to impact. Okay, so you make a note of these things. So let me remove this. So what we require now, only this final relation. So I assume that this we have taken. So let me remove. So here once again I will be writing this. Instantaneous deflection is equal to instantaneous stress square root of 1 plus, sorry, into the bracket, square root of 1 plus 2h by static deflection. Okay. Now here h is already known to us, so we have already calculated. It is 61.9 mm, right? Now what is static deflection? WL by AE. So this is also I told you theory class. So WL by AE. So W is 1000 into L, that is 3000. Cross sectional area you have just calculated. What is that? 380.1 into Young's modulus 200 into 10 raised to 3. Correct? So you will be getting 0.03945 mm if you solve this. Static deflection. That is only due to this falling weight. So complete meaning I explained you in the theory class. Just substitute this static deflection value in this equation and h value, so we will be getting determine the elongation of the bar due to impact. So this is your deflection due to impact load. So how much you will be getting? To substitute these values, 2.21 mm. So this is the answer. Okay, this is elongation of a bar due to impact, right? Or it is also called instantaneous deflection. Instantaneous deflection. So these terms, meanings, if you have any doubt, you can also refer the lecture number 1 of this impact. So again, you can revise those things and then you can come to the problems. Okay. So this is the solution for this problem. Okay. This you don't have in data handbook. Only based on that stress relation, so you can write in terms of deflection also. So how to write? So that I have just shown in previous minutes. Okay students, thank you.